So this session on flows in a rotating frame is relatively easy to motivate. If you look at the schedules for the courses this year, quite a lot of them have to do with flows in the atmosphere or flows in the ocean. And the Earth is a rotating frame, so we need to understand what effect the Earth's rotation has on large-scale fluid motion. So how do we do that? Well, we start in classical mechanics, and if you haven't seen changing of frames and what that does to the acceleration, introducing fictitious accelerations and fictitious forces, I suggest you go and look that up. But basically, our regular acceleration, which in this case, move back. In this case, this term here is our regular acceleration from Navier-Stokes. If you recall, this is the material derivative of u with respect to time, or a convective derivative, has all of these additional terms added to the end due to us being in a rotating frame. This term here is the Coriolis acceleration. And then we have a contribution from centrifugal acceleration. And then finally, we have the so-called Euler term. And this is all in a frame with angular velocity omega around the origin. So the angular velocity vector points, so for example on Earth, if I draw Earth here, here is our angular velocity vector, and here is our origin, and x is this vector that just measures the position we are on the Earth. So straight away on Earth we can get rid of this term. Ignore this on Earth, and actually for the majority of situations that you will consider in fluid dynamics, you'll ignore the effect of this Euler term because we have got steady rotation. So there's no change in this vector omega. However, these other two terms might be important, and we'll start to look at which ones we keep and which ones we get rid of on Earth. So this acceleration, this expression for acceleration, takes the place of du by dt in Navier-Stokes. So let's write down Navier-Stokes with the Coriolis and the centrifugal terms here, and see which ones remain. Now, for most atmospheric and oceanic flows, we ignore viscosity. This is because the Reynolds number is incredibly small. You can learn about the Reynolds number in the Stokes flow section of these talks. So we ignore, since Reynolds number is very, very large. Sorry, if I said it was small earlier, I meant large. I can't remember whether I did or not. Right, okay. So let's make the first consideration here. This omega cross x on Earth is going to point, if you look at it and calculate it, it's going to point either radially out or radially in. And in roughly the same direction that gravity is going to be pointing on a fluid particle. So we're going to compare this term to this term and see which one wins. So let's do 1 versus 2. Now, omega cross x scales like omega squared times a length scale. And g scales like, well, we know what g scales like, it's 10 meters per second squared approximately. Now, on Earth, omega is about 10 to the minus 4 seconds to the minus 1. This is 2 pi divided by 1 day. And length scales, well, the radius of the Earth is about 6,400 kilometers. So we'll say 10 to the 6 meters, i.e. thousands of kilometers. So omega squared L, in this case, goes like 10 to the minus 8 times 10 to the 6 over 10, i.e. approximately 10 to the minus 3. So 1 is much, much less than 2. So neglect centrifugal. Okay, The other term that's really nasty here, and that it would be quite nice to get rid of, is the non-linear term in Navier-Stokes. So as a viscous fluid dynamicist, I always want to get rid of the non-linear term. Unfortunately, can't always, but in this case, we're going to compare this term and this term. So let's do 3 versus 4. And u dot grad u all over omega cross u is what the scaling is going to be. And this goes like u squared over L over omega u, or more succinctly, u over L omega. Now actually, u over L omega has a definition. It's defined to be rho, the Rossby number. And this quantifies the relative importance of Coriolis versus inertia. Now on Earth, the Rossby number is relatively small. If we're dealing with atmospheric flows, we probably want to take u to be about 10 meters per second to the minus 1. 10 meters per second, sorry. We've got 10 to the 3, or 10 to the 6 meters, 10 to the 3 kilometers, and we've got our 10 to the minus 4 seconds to the minus 1. So actually we end up with something in this specific choice of parameters that is going to be 1/10, which I'm going to say is much less than 1. It's not all that much less than 1, so we neglect inertia. Right, what does that leave us with? It leaves us with this equation here. Now let's start thinking about the coordinates we might want to use on Earth. So this is the rotation, we'll just call this vector omega, but on Earth, so we in the UK, probably about here, we might want to set up a local set of coordinates where z points vertically, y points north, and x points east. Sorry, this is quite poorly drawn. But to omega cross u, we can then work out what effect that has in this new set of coordinates. So the assumptions that we're making are that u is mostly horizontal, i.e. most of the flows on the surface of the Earth flow parallel to the surface of the Earth to a good approximation. They're not going up or down massively quickly. So u can be approximated as being u v naught in these x, y, z coordinates. Therefore, only the vertical component of omega in the new frame, or in the new coordinates, matters. Because any horizontal component of this omega here in these coordinates, when crossed with u, is just going to disappear. So we introduce something called the Coriolis parameter, which is called f, which is going to be 2 omega sine theta, where theta here is the angle, this angle here, such that du by dt plus, and this is z hat direction, plus f cross u is equal to minus 1 over rho grad p plus g. And this g is minus gz hat in the new coordinate system. Okay, so this thing here, just as I briefly mentioned earlier, is called the Coriolis parameter. So we've got quite a nice linear in u equation for velocities on the surface of the Earth, in, say, the ocean or the atmosphere. Maybe we ought to just go back and justify why u is mostly horizontal a little bit more, if that's not an assumption you're happy with. Say we're considering the ocean. The depth of the ocean is, on the order of 1 kilometre, whereas the length scales in this direction are on the order of 10 to the 3 kilometres. So actually the majority of motion is going to be in this direction and not up or down, the most rapid motion. I'm not saying that there is going to be no up or down motion, but that motion is likely to be relatively unaffected by the rotation of the Earth. Okay, so now let's derive some equations that might be quite valid in the ocean. These are called the shallow water equations. So here we are left with the equations that we derived earlier. Remember, this F is 2 omega sine theta, where theta is the latitude, and U is equal to this. So let's work this out in components and see what we have. So our x component, du by dt minus fv, is equal to minus 1 on rho dp by dx. There's no contribution from g in the x component. The y component, dv by dt plus fu, is equal to minus 1 on rho dp by dy. That's the y component. And then finally the z component, there's no velocity component and there's no component from f cross u, because remember f is in the z direction itself, is equal to minus 1 on rho dp by dz, and then there's going to be a minus g. Okay, so let's solve this one first. We know that the pressure on the surface of the shallow water is going to be P0. We assume that's uniform on the surface. So we can solve this to get the pressure is equal to P0 plus rho g h minus z, where h is the height of the surface, and this is some function of x, y, and time. Okay, so we can then plug this into these two equations, this expression for P, and we're left with du by dt minus fv is equal to, well, what's dp by dx? dp by dx is just going to be rho g dh by dx, and likewise for dp by dy. So this is going to be equal to minus g dh by dx. And similarly, dv by dt plus fu is equal to, in this case, minus g dh by dy. Okay, and these things here are called the shallow water equations. They're very helpful for solving quite a lot of flows involving thin layers of fluid on a rotating frame, or in a rotating frame, like, for example, large-scale ocean movements. We're going to now take these two shallow water equations and consider something called geostrophic balance. This is the steady case. So flows aren't changing, so du by dt and dv by dt are 0. Okay, so these equations therefore suggest that v is equal to g over f dh by dx, and u is equal to minus g over f dh by dy. Now, if I write this in the form u is equal to minus d by dy gh over f, and v is equal to d by dx gh over f, this looks somewhat familiar, or it should begin to look somewhat familiar, because gh over f, or rather minus gh over f, is actually acting as a stream function for the velocity field. So remember that when we have a stream function, u is d psi by dy, and v is minus d psi by dx, where psi is equal to minus gh over f. Now, this means lines, remember thinking back to streamlines, lines where psi is constant are streamlines, i.e. the flow flows along lines psi equals constant. That means that the contours of h, contours of the height, are streamlines for the flow. This is a very handy result that results from considering steady flows in a rotating frame, having made the assumptions we've made. And with these tools, you can solve most of the problems that we're dealing with in rotating fluids that you would have seen coming up to part 2 of the mathematics tripos here at Cambridge. Another handy result here is that obviously streamlines are also contours of P. Since P is P0 plus rho g h minus z, and contours of H, same as contours of P, at a given height. So yeah, we've now seen the rotating frames equations, the shallow water equations that result, and then considered geostrophic balance when flows are steady. If there's anything there that needs more clarification, or any of the problems on the example sheet that you have received that are causing you trouble, drop me an email. These two references are really great for flows in a rotating frame. The final chapter of these notes here covers exactly what I've covered, maybe in a little more depth, so that's probably worth a read. But if there's anything in there that causes you any trouble, please do bring that question along. Thanks a lot.